So hello everyone again. This is lecture 5 part 1 of alternating current. In the previous part we are on the just last question regarding the concepts of concepts after resonance were being completed. So let's discuss that question and then we can move on with the next concept, that is power factor. So this is lecture 5 part 1 of alternating current. I am Sameer Lavankar. Let's begin our discussion. So currently the course outline for you, we are on the 6th topic, that is AC voltage applied to a series LCR circuit, in which we have understood two subtopics also, which is resonance and sharpness of a resonance. Before that we have started with the discussion regarding introduction, then AC voltage applied to a resistor, then the phasor diagrams in the third topic, that is representation of AC current and voltage by rotating vectors, then AC voltage applied to an inductor, then AC voltage applied to a capacitor, and then currently we are on the 6th topic, that is AC voltage applied to a series LCR circuit. Once this is completed, we can move on to the 7th topic, that is power in AC circuit, that is power factor, and finally to the last two applications part, that is LC oscillations and transformers. So let us begin the discussion directly regarding the last thing which we have left in the last part. Okay. So this was the question in which first of all we calculated the value of current. The current value which was calculated was nothing but equal to V upon Z, where Z is the impedance. How was impedance calculated? As the impedance was only and only due to capital R and XC, therefore the impedance was calculated as equal to root over R square plus XC square, correct? When we calculated its value and then divided that value by in denominator with numerator as 220, we got the value of current as 0.755 amperes. Right. Then the next question states that the question asked was calculate the voltage across the resistor and the capacitor. Is the algebraic sum of these voltages more than the source voltage? If yes, then we need to resolve the paradox. Okay. So quite evident, we completed till the first part only. So let's just revise the first part. So in the first part, the value of the voltage across the resistor is nothing but equal to capital I into R. Therefore, it is nothing but 0.755 into 200, which is 151 volts. For capacitor, the value is I into XC, which is 0.755 into 212.3 ohms, which is 160.3 volts, correct. If you sum the value, you are getting the answer as nothing but 311.3 volts, correct. But this 311.3 volt was not coming out to be equal to 220 volt. So what was the reason behind it? So the reason behind it is simply that, so let me write that here. So the algebraic sum of the two voltages, what are the two voltages here? They are VR and VC. Okay. So the algebraic sum of the two voltages VR and VC is coming out to be more than the source voltage. Okay. Now why it is coming out? Let us resolve that paradox. So basically, as we know that we have learned before that these two voltages are not in phase. The voltages across the resistor and capacitor are not in phase, right. So therefore, as they are not in phase, they cannot be added as scalars, right, or we can write it as ordinary numbers. So basically directly cannot add if we need to find the value as 220 volt, correct, because there is no use of doing like this. So because they are always, so as these voltages are out of phase, by 90 degrees. Therefore, we can simply use the Pythagoras theorem. If the value would have been somewhat different, then we would have used the formula under root of a square plus b square plus 2ab cos theta. But right now, as that is not required, so therefore, if we need to actually sum up both of them, the actual summation would come out to be root over Vr square plus Vc square. If you try to sum up this, so it is basically nothing but 151 square plus 160.3. 160.3 square. So, when you try to do the calculation here, you will get the answer as nothing but equal to 220 volts, and that is how you need to solve for this paradox, or basically how this sum of voltages appear. So, actually the algebraic sum of these voltages has no significance, has no value here. The actual way to calculate the value of summation, or let us say these complete source holds or this complete circuit holds, is nothing by using the actual values of phasors, and due to the use of these phasors we can directly implement the value of what we can say the sum value. Now, this sum value is basically not algebraic sum value, it is vector sum value. Okay. So, that was the concept here, that was the final resolve. So, that is how the paradox is being resolved here. Okay. So, that thing being said, I think that is the end of this concept. Now, let us move to the new concept, very important concept as far as this chapter is considered, that is power in AC circuit. Okay. So, power, as the name suggests, we are just trying to calculate the value of power, but because there is a change due to the change in the DC circuit change into AC circuit, therefore, we will understand a new concept or new definition which is called as power factor. Okay. Simple concept, simple definition, but it is very important to understand this. Okay. So, let us understand it line by line. Okay. So, we have seen that a voltage V is equal to Vm sin omega t applied to a series LCR circuit or RLC circuit drives a current in the circuit which is given by I is equal to Im sin omega t plus phi, where we have just calculated, we have divided completely into using two different ways. One was using phase difference solution and second was using general solution. Okay. So, basically the general solution was being implemented or derived using the analytical solution, and the phase driven solution basically gave us the steady state solution. Okay. So, finally the input was that the first assumption was that V is equal to Vm sin omega t, and we obtained or we generalized the solution initially that I is equal to Im sin omega t plus phi. We just needed to calculate the value of Im and we needed to calculate the value of phi. Okay. After complete derivation, we got the value of Im as equal to Vm by capital Z and phi as tan inverse of Xc minus XL by R. So, this L should be in subscript. Okay. So, it is nothing but Im is equal to Vm by capital Z and phi is equal to tan inverse Xc minus XL by R, where what is the value of Z? Just for a quick revision, it is nothing but root over R square plus Xc minus XL whole square. Fine. Okay. Now, let us calculate the instantaneous power. So, what is instantaneous power? As the power suggests, what is the formula for power? Power is nothing but a product of V and I. Okay. So, P is equal to V into I, therefore, it is Vm sin omega t, which is already assumed, into Im sin omega t plus phi. Okay. Just put Vm Im outside. So, when you try to solve this equation, you will get, after applying trigonometric identity here, you can get this as similar to Vm Im by 2. Again, this Im is in subscript, sorry for this correction. Vm Im by 2 into cos phi minus cos 2 omega t plus phi. Okay. Now, let us try to calculate the average power. So, this is the instantaneous power, this is the instantaneous power, you may remember this directly. To calculate the average power, we know that we need to just check for this complete in the complete cycle, we need to find the average, and that is our answer, right. If you remember correctly, for the power in an AC source through a complete inductor or a capacitor is always 0, but the instantaneous power is not 0. We had some value for instantaneous power, but the average power over one complete cycle was always 0 for inductor and a capacitor. Okay. So, the average power over cycle is given by the average of the two terms in RHS of above equation. It is only the second term which is time dependent. As you can see, cos phi is time independent. So, even if you do the cos of average of this, it will come out to be 0. But because this term is time dependent, we cannot directly find the average as in for the complete cycle. We will try to do some different variation and try to see what happens. Okay. So, it is only the second term which is time dependent, its average is 0. the positive half of cosine cancels the negative half. Okay. So, here also what was observed, that it was observed that even if you do it with time also, after a complete cycle is being formed, either this is the diagram or either this is the diagram, even if this happens for a complete cycle. So, when the time t is from 0 to 2 pi, then after 2 pi variation is being done, after that always the value of average power produced over a complete cycle is 0. Okay. Therefore, finally what we got the value of power as? We got the value of power as nothing but equal to Vm by 2. Okay. So, the basic crux is simply that the value of cos phi average is neglected and only the value of cos average due to this cos 2 omega t plus phi, basically the dependent term gives you the value as 0. Okay. Okay. So, P is equal to Vm Im by 2 into cos phi, which is equal to Vm by root 2 into Im by root 2 into cos phi. So, we are just trying to change it so that we can convert these forms into IRMS values and VRMS values. So, we already know, so it was in the starting introduction of this chapter, as in why Vm by root 2 is capital V and why Im by root 2 is capital I. Okay. So, this is Vm by root 2 into Im by root 2 cos phi, which can be converted into capital V into capital I into cos phi. Now, this can also be written as how? So, basically we know that V is nothing but equal to Iz, therefore, we can write this as equal to P, which is equal to I square Z cos phi, fine. So, now please refer to this very carefully, because this is the main crux here for this concept. So, the average power dissipated depends not only on the voltage and the current, but also on the cosine of the phase angle between them. Please remember this very carefully. Okay. First of all, please remember that we are talking about which form? We are talking about that circuit which has a series LCR circuit. Please remember the first assumption. The second assumption being made was when we try to assume the value of voltage sinusoidal form, it is assumed as V is equal to Vm sin omega t. Okay. Let us say a complex question comes in which the value of Vm was given to you as Vm cos omega t. Then there is a chance, means we need to derive and see that the value of power coming is same as this or not. Okay. So, please remember these assumptions also, these assumptions are also very important. Okay. So, this is the power factor, or this is the value of power being obtained when first of all the circuit used is LCR circuit, and second thing is when the value of V is nothing but equal to Vm sin omega t. Okay, fine. So, now the thing is that after calculation, after this derivation, we found that the value of P is nothing but equal to I square Z cos phi. If you look at this very clearly, it is a product of square of I into Z, that is the impedance, into cos of phase angle, correct? Please remember this. Okay. So, the average power dissipated depends not only on the voltage and current, but also on the cosine of the phase angle between them. Okay. The quantity cos phi is called the power factor. Okay. So, this is the new terminology. As I already said, the value is little easy to understand, but the concept is little tricky to understand, as in why this value of cos phi is coming. Okay. So, the quantity cos phi is called as the power factor. Now, let us discuss different scenarios of what will happen with different cases. Okay. Fine. So, now what happens in resistive circuit? As the name suggests, resistive circuit, that means only and only R is present. That is the second concept which we try to understand in this chapter. Okay. So, if the circuit contains only pure capital R, it is called resistive. In that case, phi is 0, cos phi is 1, and there is maximum power dissipation, because cos phi value of 1 is the maximum value which cos phi can attain. Okay. This is your case 1 being done. Moving on to case 2. So, case 2 is purely inductive or capacitive. That means the value of R is not equal to means R is 0, but other values exist. Okay. So, purely inductive or capacitive circuit, if the circuit contains only an inductor or capacitor, we know that the phase difference between voltage and current is pi by 2. Okay. It is very clear, we have already understood these all concepts in the ideal circuits being understood. So, basically we understood about inductor as an individual sense, we also understood a capacitor as an individual sense. Okay. So, purely inductive or capacitive circuit. So, if the circuit contains only an inductor or capacitor, we know that the phase difference between voltage and current is pi by 2. Okay. Therefore, cos phi is 0. Why is cos phi 0? Because we know that the value of phi is 90 degree. If phi is 90 degree or phi is equal to pi by 2 radians, we know that the value of cos phi is 0. And hence, there is no power dissipated even though the current is flowing in the circuit. the current is sometimes referred to as wattless current. Why it is wattless current? Because the unit of power is watts, and because the value of power obtained with different values of V and I is always 0. If it is 0, it is said to be wattless. Okay. So, till now 2 circuits were being obtained by us. So, first of all, please remember this phi angle is the angle between the phase difference between V and I. There is no relation between the phase difference, let us say for R and C or C and L. Always and always this phase difference refers to the value of difference between the phase angle between the voltage and the current passing in the circuit. Please remember, if the current passing through the circuit is Im, let us say it is LC circuit or LCR circuit, always the current will be passing the same through the complete circuit. So, there will not be any change. Please do not get confused regarding these concepts. Please remember, phi is always the phase angle between the voltage and the current. Okay. Okay, then the first concept we understood was about resistive circuit. So, for resistive circuit the value of cos phi is 1. So, maximum power is being generated, and for second, when the value of R is 0, basically as cos phi is pi by 2 or either minus pi by 2 or plus pi by 2, the value of cos phi is 0. Okay. So, that was the second circuit. Now, let us move on to the most general circuit, that is LCR circuit. What happens in an LCR circuit? In an LCR series circuit, power dissipated is given by previous equation, which is phi is equal to tan inverse XC minus XL upon R. So, phi may be non-zero in a LR or RC or RCL circuit, right? Quite evident, because you may get some value of XL and R, you may either get the value some as XC and R, you may either, because R is always a positive quantity and either of this may exist or both may exist, then there is 100% scenario that there will be value of phi as long as XC is not equal to XL. Okay. So, this is the third case, that is phi may be a non-zero in a RL or RC or LCR circuit. Even in such cases, power is dissipated only in the resistor. This is very important line. This may be asked in MCQs also. Always remember, XC and XL do not dissipate power. Every time the work of power dissipation is only in the hands of resistor. So, if there is no resistor, no power will be dissipated. Okay. Fine. That thing being said, let us move to the final case. What is the final case? Final case is just that when XC is equal to XL. So, power dissipated at resonance in an LCR circuit, at resonance XC minus XL is 0 and phi is 0, correct? Because if you put the value of XC is equal to XL here, you will get the value as phi is equal to 0. Therefore, cos phi is 1 and P is equal to I square Z, which is equal to I square R. Quite evident, it will again change into first case scenario only, and therefore the maximum power is dissipated in a circuit at resonance. Okay. So, when the question may arise again, means in exams, when is maximum power being generated? It is first of all generated in a purely resistive circuit, and second is generated in an LCR circuit when there is resonance. Please remember, resonance only and only occurs in an LCR circuit. It cannot occur in an LC or LR circuit. Okay. And even RC circuit. Second concept is that for purely value 0 power, it should be a purely inductive or a purely capacitive circuit, and some sort of generation when it is required, which is less than the power being generated, it is always in an LCR circuit. But please remember, in an LCR circuit, if a power is being generated, the power is only and only dissipated through a resistor. Fine. So, let me stop the discussion here only. We will understand more and more about these using the example given here, and then we can move on to the next concept. Okay. So, let me stop it here. Thank you so much.